All right, let's jump right in. Have you ever stopped to wonder how your phone, your laptop, literally every smart device you own actually thinks? Well, it turns out they all speak a secret language, a foundational logic that's surprisingly simple yet incredibly powerful. And today, we're going to decode it.
I mean, seriously, think about that for a second. At its absolute core, every computer is just a giant collection of switches that are either on or off, 1 or 0. So how on earth do we get from that simple binary choice to streaming movies, playing games, and doing everything else we do online? That's the puzzle we're going to solve today.
Everything starts with what we call a digital system. It's a fancy term for something that takes a bunch of simple inputs, our ones and zeros, and through a maze of circuits, spits out a useful output. But here's the catch. As these systems get more and more complex, they can become unbelievably inefficient, slow, and crazy expensive to build. And the answer, the secret weapon engineers use to cut through all that chaos, is a beautiful system of logic called Boolean Algebra. It's the tool that tames the complexity and makes all of our modern tech possible. So first up, let's get into the computer's simple language and really understand the basic building blocks of this whole thing.
So what is it exactly? Well, Boolean algebra is basically a set of rules where every variable can only have two values, true or false, on or off, 1 or 0. And its number one job, the whole reason it's so critical in electronics, is for one main purpose, minimization. It's all about taking something complicated and making it elegantly simple.
Okay, next, let's learn the 3 basic rules. You can think of these as the fundamental verbs of this digital language.
First up, we've got the easiest one of them all, the NOT operation. It's also called inversion, and it does exactly what it sounds like. It just flips the value. If you give it a 1, you get a 0. If you give it a 0, you get a 1. It's like a light switch. That's it.
And you can see it right here. That little bar over the A, that just means not A. So a 1 with a bar over it becomes a 0. A 0 with a bar becomes a 1. It really is the most basic building block in the entire digital world.
Next up is our second rule, the AND operation. Now this one is a bit more strict. For the final output to be 1, or true, every single one of the inputs has to be 1. It's like trying to start a car. You need the key in the ignition and your foot on the brake. If you're missing even one of those, the car won't start.
This truth table tells the whole story. Just look down that output column. The one and only time we get a 1 is in that very last row, where input A is 1 and input B is 1. Every other combination, the result is 0.
And our third and final rule is the OR operation. This one is way more forgiving than AND. To get a 1 as your output, you just need at least one of the inputs to be a 1. It's like someone asking if you want cream or sugar in your coffee. You can say yes to one or the other or even both, and the answer is still yes, you're having something.
And the truth table makes it crystal clear. The only way you get a 0 is if both inputs are 0. If there's a 1 anywhere in the inputs, the output is a 1. And that's it. Not, and OR. That's the entire foundation of all digital logic. Pretty wild, right? Okay, so we've got the basic rules down. Now for the really cool part. Let's see how we can use these simple tools to do something amazing. This is where we go from complex to simple, and where the real magic happens.
So an engineer might start out with a logical expression that looks, well, like this. It's kind of long, a little messy. You see all those letters? All that's saying is y equals A and B, or A and not B and C, or A and B and C. Yikes. To build this in the real world would take a lot of physical parts. It's complicated.
But then, what happens if we take those 3 simple rules we just learned, the NOT, the AND, the OR, and we apply them to this beast of an expression?
It boils down to this. The entire thing, that whole long, tangled equation, was just a super complicated way of saying A. Can you believe that? All that complexity just collapses into a single letter. Y equals A. That is the incredible power of this stuff. Now, you could always work through these long expressions by hand, but that would take forever. So engineers have developed these amazing shortcuts called theorems. Think of them like cheat codes that help you spot patterns and simplify logic in a flash. And to see how this works, let's just check out one really useful example. It's called the consensus theorem, and it is a fantastic tool for cleaning up your logic.
What this theorem shows is that in an expression like this one,
That very last part, the BC, is totally redundant. It's like dead weight. Its outcome is already covered by the other two parts of the expression, so it adds no new information. And because of that, you can just get rid of it. A brilliant shortcut to a much cleaner result.
So, okay, we can make equations shorter. We can make them look prettier on a whiteboard. But who cares, right? Why does this actually matter in the real world? What's the real payoff for all this work?
Yeah, that's the crucial question, isn't it? What do we actually gain from doing all this? Why do engineers spend so much time on it?
Here's the payoff. It's huge. A simpler expression means you need fewer physical logic gates on a microchip. That directly means the chip runs faster, it uses way less power, and it costs a lot less to manufacture. It even reduces something called fan-in, which just means the whole system becomes more efficient and reliable. And that's what this all comes down to. You go from abstract math on a page to a very real, tangible result that you can feel every day. It's a faster, cheaper, more powerful phone in your pocket. That's the real-world impact of Boolean algebra.
So I'll leave you with this final thought. The entire digital universe, from the simplest calculator to the most advanced AI, is all built on these same simple rules for cutting through complexity. It kind of makes you wonder, doesn't it? What other big, messy problems in our own lives could be made just a little bit simpler if we learn to think with this same kind of clear, fundamental logic?